Check it out now, y'all.
nanoHUB-U, online instruction.
So welcome to the second module for this week, that's 4.2. And as you remember from module 1, what we were trying to discuss is how you go about writing these matrices when you include the spin. And we took this simple example where, this is just a one-level device, one level but with two spins, so it's like two levels really. And we saw that the H would be a 2x2 matrix. And this connection to the contacts, the gamma, it could be gamma 1 or gamma 2. We said that a simple way to write down would be that it's equal to some number alpha for the spin that is in the direction of the magnet. If the magnet, let's say, is in the z direction, then that's this alpha. And then opposite to that direction, it would be the beta. And what we want to discuss in this module is how you'd write this down if your magnet was in some arbitrary direction. You see? Here it's like, okay, if it's in a particular direction z, we have got this written. What if it was not in the z direction, some other direction? And what we'll show is, actually, so let me just state the result first, because this is very new, and if you haven't seen this before, it will take some time to get used to this, and that's what we'll be going through in the next few modules, actually. Okay, let me first write this in a slightly different form. You see this gamma, the way we have written this, you could write it in a form that looks something like this. Gamma is equal to alpha plus beta over 2 times 1 plus p and 1 minus p, 0, 0. So this is actually, all I've done is a little algebra. That is, you take this and you can write it in this form. And I'll explain what is this p. The p is what you call the polarization of the magnet. And this is where, if you remember, back in, I guess in the part 1 of this course, that's, if you're looking at the notes, that's what's called the lecture 14. There we had defined P as this, in terms of this resistor model. It was like R up minus R down and R up plus R down, that ratio. In this context, the natural way to discuss polarization would be, or define polarization is like alpha minus beta over alpha plus beta. And as, if you are interested, if you look at the first tutorial, there I try to explain why these alphas and betas are kind of like conductances actually. So in that sense, you could say this is like the ratio of conductances, of this difference in conductance divided by that. And polarization, the idea is if you had a perfectly polarized magnet, then you see only one type of spin would be able to get out and the other wouldn't be. In that case, beta would be 0. So one type, the minority spin wouldn't be able to get out at all. And if beta is 0, you get a polarization of 100%, as you can see. So now if you define it this way, then you can see why this line is really the same as that line. Because if you multiply alpha plus beta over 2 times 1 plus p, what you get is, the first term is alpha plus beta over 2, and then the second term is this p, which is alpha minus beta divided by alpha plus beta. So let me just write that here. And you can see when I add those two, what I get is alpha. So that's exactly what we had here. So in that sense, we have just taken alpha and written it in this way. See? So this is the result then from the last module, just written in a slightly different way. And if we reverse the magnet, that's almost like making the polarization negative. And in that case, you'd have a 1 minus p there and a 1 plus p there. And as we discussed in the last module, you'd have a beta here and an alpha over there. Okay. Now, question is, how do we write it when magnet is in some arbitrary direction compared to the z, what we call the z direction or standard direction? And the result that basically what we'll be doing in this module is that the correct answer, let me just write it here, will be gamma is equal to alpha plus beta over 2 times 1 plus pz, 1 minus pz. That means I now have a magnet that points in some arbitrary direction, that's like a vector, and it has a z component. So I could take that polarization times the component of it in that direction. But now you also have a px, py, etc. And those will enter as off-diagonal terms here. You'll have a px minus ipy and a px plus ipy. And now P is like a vector whose magnitude is like what we had before, alpha minus beta over alpha plus beta, but it is a vector which also has a direction. And that direction is this unit vector in the direction of the magnet, some n. That's some direction of the magnet. Okay? So this is now a vector like this, and the corresponding gamma will look like that. So this is what I'll be trying to obtain in this module, or show you where it comes from. Okay. And this needs a somewhat different concept that I need to introduce. And when you represent spins, one of the points I think I had made again in the part 1, that the nearest thing to spin is that we know, that we are probably familiar with, is this polarization of light, which you usually think of as vectors. A vector that points in some direction. And one of the points I had made is that when you have a polarizer and an analyzer, usually the light that goes through is proportional to cosine squared theta. So if you have polarizer and analyzer at 90 degrees, it blocks light completely when it's 90 degrees. On the other hand, with spins, in order to block things, you have to be 180 degrees. You have to be anti-parallel. So current flows when it's parallel, but if you want to block it or minimize it, you have to be anti-parallel. And this is reflected in the idea that when you have vectors, if you had a vector in a zx plane, let's say this is z and you have an x, and if you have a vector in this zx plane at an angle theta, then you'd write its components as cosine theta and sine theta. Whereas, when I'm thinking in terms of this upspin and downspin, the components of this quantity that points in this entity that points in some direction theta, the components are cosine half theta and sine half theta. And this is what leads to that basic difference that I had mentioned. That is why with vectors, 90 degrees stops things. With spinners, it's like you have to be anti-parallel to stop it. That's the basic thing. Okay. Now, just to generalize it a little bit, generalize meaning, this is if it's in the zx plane. What if you had z, x, and y? Then you often describe a vector pointing in some direction in terms of two angles. One of them is this angle theta, which is in the zx plane, which tells you the angle from the z. And then you project it down on the xy plane and look at the angle from x. So you usually have these two angles, phi and theta. And in terms of that, you would usually write the z component would still be cosine theta. That's the vector's component along z is still cosine theta. But the x component now would be sine theta and then a cosine phi. And the y component would be sine theta, sine phi. So this is the kind of thing you have seen when you have learned vector algebra, that if you had a vector in some direction theta phi, those would be the components. Now what is new, and that is when you're writing in terms of the spinors, you have these two components, cosine half theta and sine half theta. And the way this extra angle phi enters this is, there's a e to the power minus I phi over 2 here, and there's a e to the power plus I phi over 2. So when you think of vectors, it has got 3 real components. When you think of this spinor, it has 2, the way you represent it is with 2 complex components. These are complex numbers. Now this of course isn't meant to be obvious. This is the whole new thing that I'm trying to get across in a way this week. And right now what I'll say is, if you accept this, then you'll see how everything else follows, which is what we'll be doing in, say, this module and the next. And then a couple of modules later, I'll come back and try to justify it a little bit better. In the sense, I'll try to say why, how you could, what exactly is behind this particular representation. Now, this components of vectors, that of course you have seen for a while. I mean, that's something you see first in as a freshman possibly, or even earlier, whereas this is totally new. But at this moment I'm saying, let's just accept it and let's see how other things follow from it. Now, so this quantity then, I'll just write as C. That's the cosine theta over 2 exponential minus I phi over 2. And this quantity I'll write as S. And one thing you can show is, so this represents a spin that is pointing in this direction. Now if you had a spin that was pointing in exactly the opposite direction, so this is the direction n, some funny direction. Now if you had something that was pointing along minus n, then you could work out the thetas and phis that represent something in the minus n direction. And with a little thinking, this isn't completely obvious, takes a little thinking, you could show that the corresponding components would be minus S star and C star. The way you get it is by, instead of theta, you sort of put in pi minus theta, and instead of the phi, I think it would be like pi plus phi. So these are the components of n, and these are the components of minus n. And this is kind of what I need for the next step, which we'll be doing. And so remember, the original purpose was, well, how do I write down the gamma for a magnet that is pointing in some arbitrary direction, n. So let's say this is a magnet that's pointing in some direction, n. How can I write down the gamma corresponding to that? And what I'll do is, I'll make use of this to obtain that result. That's what we'll be doing. Okay. Now, first step is that this is where I'll be using this concept of basis transformations in matrix. That when you have a matrix, you can transform it into another basis. And this process of transformation, that's what I'll be using here. So let's say we first want to write gamma in the basis of n and minus n. So it is as if, I said that, well, the gamma is very easy to write down if, let's say, the magnet were pointing in the z direction. Then it would have been just alpha and beta, 0, 0. You know that. That we did last module. So if it was in the z direction, the problem is that it's now in some funny direction n. Now the point I'm making is that we could always have taken that n direction and called it our z, sort of. So as long as I'm using n and minus n as my basis, gamma should look like this. And my problem is simply how to transform this into the basis of z and minus z. And there the rule is that, well, you have to take that matrix and multiply it with 2 matrices, one on front and one at the end. The one on this side is a matrix that looks like this, where it takes this n and minus n, those are our basis functions for this one, and expresses them in terms of z and minus z. So that's one matrix. And the other matrix is one which it does the opposite. takes Zn minus Z and expresses them in terms of Nn minus N. And actually, if you have this matrix, you don't really have to think hard to write that one, because this one is actually the conjugate transpose of this one. So this is the basis transformation principle that I'm drawing from theory. If you have taken a course in linear algebra, you have probably seen this, but if you don't remember it, this is something you may want to brush up on. So the way I remember this is that these matrices have to be written such that what appears here must match what appears here, because that's the rule of matrix multiplication. Columns get multiplied into rows. Similarly, what appears here must match that. So how do I write this matrix then? Well, the question is, if I had a spinor pointing in the n direction, what would its up and down components be? Zn minus Z components. And that's what I said, I stated without proof. As I said earlier, what I'm going to do is ask you to accept this and show that the rest follows. And then later come and try to make this seem a little more reasonable. But if you accept this then I've got C and S. That's it. And for minus N, you got minus S star and C star. That's this matrix. Okay. That's one. And then I had this matrix from before. And then this matrix, as I said, is the conjugate transpose of that, which means it looks like C star, S star, minus S, and C. That's it. So this was gamma in the original basis, namely in the Nn minus N basis. That is like whatever direction the magnet is pointing, if I had considered that direction as my up and down, then whatever I'd have got is here. But then, of course, my standard for everything is that the up and down should be this Zn minus Z. And so I need to transform it. And the way you transform it then is through this, what's called a unitary transformation or coordinate transformation, basis transformation here that we have written, n's in terms of z's and that. Now from here, what I'll need to do is just multiply this out. And after that, it's just algebra to get from this to that, which is what I'll be doing for the next few minutes. But basically, I'll just be multiplying it out and doing some algebra. But the essence of it is right here. Conceptually, this is it. You see? Okay. So let me try to multiply this out then. Take this off from here. So when I multiply those two, I get alpha times C star, 0 times S, that's 0, alpha times S star, minus beta times S, and then beta times C. So I've multiplied those two, and I have to now multiply this one. C minus S star, S, C star. That's what I have to do. So let's try to multiply this out. So now the first term will be this times this plus that times that, which comes to alpha times CC star plus beta times SS star. Now this one is CS star times alpha, C S star times alpha, and then minus CS star times beta. So that's a beta. Then SC star times alpha minus beta. And here you have alpha SS star plus beta CC star. Okay. Now, okay, so I'm done here. Now, you'll remember what the result we were trying to get was something like this, that this thing after you're all done should look like alpha plus beta times this 1 plus pz, px minus ipy, px plus ipy, and 1 minus pz. Okay? That's what I was trying to get. Now you can see easily with a little algebra right now that this is indeed giving you that. So let me show you that. So what is this CS star? That's where we need to go back to how we define these things. So that's C. And this is S. So when I take S star, that is like sine theta over 2 and e to the power minus I phi over 2. So when I multiply these two things, so I take CS star. Let me take this off. So when I take C times S star, what I get is cosine half theta, sine half theta, and then e to the power minus I phi. And that's equal to, this is like actually half of sine theta. So it is half of sine theta, and e to the power minus I phi is cosine phi minus I sine phi. And if you, I guess the vector components I just erased from here, if you look there, you'd see the sine theta cosine phi, that's like the x component, and sine theta sine phi is like the y component. So this is sort of like half of the x component of x minus I times, x component of this vector n, this unit vector that we are talking about. If you looked at the x component, it would be sine theta cosine phi, that's this, and then the y component of n. So the point is, oh, by the way, I think when I wrote here, I missed a half there. That would be this half. But otherwise, you can see what happens. This alpha minus beta, if I divide it by alpha plus beta times alpha plus beta here, then this is what is P. And what I just showed is that this CS star is like nx minus I ny. So that's how you get the px minus ipy. Similarly, if you looked here, you'd get the px plus ipy. And these are all, written out clearly in the notes. So you could go back and look at it. I'm just trying to show you roughly how you get those things. Now, if you look at these diagonal elements, then you can see it's a little different. That now you are involved with CC star and SS star. So when you take CC star, what you get is CC star. Now you see the phase factor drops out, so all you get is cosine square half theta. And SS star is like sine square half theta. And cosine square half theta is again half of 1 plus cosine theta. And this one is like half of 1 minus cosine theta. And again, if you look at the vector components, cosine theta is of course just the z component of that n vector, of that unit vector. So it's really the z, and this one is like z, same thing, z component. So once again, if you took this, you would get this alpha plus beta over 2 times 1 plus pz. That comes from this 1 plus nz type of thing. So this is, again, as I said, the details are written in the notes, you can follow. But what I wanted to show you then is, roughly, that how from that basis transformation, you get this final result here. And the final result is that if I have a magnet pointing in any direction, and I want to write down the appropriate gamma that tells me the connection of the channels to the contact, the way you would write it is, the final answer is this one, that this P is the polarization of the magnet. Its magnitude is given by alpha minus beta over alpha plus beta. That's the magnitude of it. And the direction is the direction of the magnet. And so what you put here is PZ, that is P times the component of the unit vector along the z direction, unit vector in the direction of the magnet. Similarly, here is px minus I py, etc. And if you didn't have these x and y components, the rest is sort of intuitive. In a way, if you just took 1 plus p and 1 minus p, that's kind of what we had in the last module, without all this fancy stuff. And that's why as long as everything is in z direction, as long as all your magnets are collinear, you can always take that direction as z and thereby avoid all this complexity. But if you have magnets in multiple directions, then of course you can take one of them as z, but the other one you have to deal with the fact that it's not in the z direction. And then you really need all this extra things that we are getting into now. And that is why the description we had back in part 1, week 4, that applies for what you often call collinear magnetoelectronics. That is where all magnets are kind of in the same direction. Some parallel, some anti-parallel, but they're all in the same direction. And that direction you can choose as z. Okay? But what we now are developing is the machinery that allows you to handle problems where magnets are in arbitrary directions. And of course, to use these NEGF equations, the important point is how to write these matrices. And what I just described to you is how you'd write the connection to the contact if the contact is a magnet in some arbitrary direction.